तो आज की प्रॉब्लम है एथिल बेंजीन की प्रॉब्लम है। तो आप लोग सबको प्रॉब्लम स्टेटमेंट मिल चुकी है। प्रॉब्लम स्टेटमेंट के अकॉर्डिंग सबसे पहले हम ऐड करेंगे कंपोनेंट्स। तो कंपोनेंट उसमें है इथेन, इथाइलीन, बेंजीन, एथिल बेंजीन, एंड डाई एथिल बेंजीन। पैरा डाई एथिल बेंजीन रीनेम कर लेंगे इसको। Then method is Chaucer as written in the problem statement. Run the problem. Now you are done with this properties environment. And now go to the simulation environment. In simulation environment we have CSTR reactor. The operating condition of CSTR is 20 bar and 150 degree centigrade. सो फ्रेश बेंजीन जो कि एक बार पे आपके पास है तो पंप पे जाएगी, देन प्रेशर ड्रॉप के लिए वॉल्व, देन सेंड टू द रिएक्टर. Since reactor have 1 degree of steady state degree of freedom, so there is a one wall outlet of the reactor, and ethylene is in vapor form, so there is only uh, one valve for to reduce the pressure of the ethylene stream. So this one is your fresh benzene, this one is your fresh ethylene, then benzene in, and this is ethylene in, and this is CSTR out. This is CSTR. So feed condition of benzene is 25 degree centigrade, 1 bar, 100 kilomole per hour, and mole fraction is 1 for benzene, and for ethylene is 25 degree centigrade and 25 bar, 105.26, and mole fraction is 0.05 ethylene and 0.95 ethylene, 0.05 ethane. Then we have to increase the pressure from for benzene stream, and then we have to reduce the pressure to 20 bar because the reactor inlet pressure is 20 bar. Similarly for ethylene stream. Reactor condition 20 by 150 degree centigrade, and liquid only. Reactor volume is 200 meter cube. It is given in the problem statement, and then we have to write the reaction. So for reaction you have to come to the reaction environment here, and select power log reaction, and then add all three reactions. That is, ethylene react with benzene to give ethylbenzene. A coefficient for reactant coefficient should be -1, and order of reaction, that is exponent, is 1. It is given in the problem statement, and for product coefficient is 1 and there is no exponent. Then your ethylbenzene react with ethylene to give diethylbenzene. There is a side reaction, and the same way it will be written. Then your trans-alkylation reaction, diethylbenzene react with benzene to give ethylbenzene. Hello. Then we have to give the kinetics of the reaction. So for the first kinetic, as written in, as given in the problem statement, the exponential factor is 1.528 10 to the power 6, and activation energy is 17,000 calorie per mole, and reaction basis is molarity in concentration, and second reaction is 2.778 e to the power 7, and activation energy is 20,000 molarity, and for third reaction K is 1000 and activation energy is 15,000. Then we have to add this reaction to CSTR. So we go to the CSTR and add in here reaction, and then run the problem. After running the problem, you will get this. Your benzene is converted. 100 benzene, approximately 77% benzene is converted to ethylbenzene and diethylbenzene. So for the remaining benzene, we have to add one more CSTR. Or for the remaining ethylene, reactor, CSTR, add, and since there is 1 degree of freedom, so we have to add one valve also. Pressure drop of 5 bar. Same condition, 20 bar and 150 degree centigrade, and reaction volume is 200 meter cube, and reaction is same. After this, rename it CSTR2, and this is out. React, you can see benzene is 13, ethylbenzene is 23, and diethylbenzene is 13. After the reaction part, first column, the work of first column is to let out the unreactive ethylene and ethane, unconverted inert ethane, from the top of the column. So we use the red flag column. In red flag column, there are total of 11 stages, 10 stages and one revolver stage as given in a problem, and it will be a partial vapor because ethane is vapor form, so it will be come out as a vapor. So and total flow rate of ethane, as you can see in CSTR2, it is 5.263. so the first case should be the approximately equal to the total ethane. I will give it 5.29, and reflux ratio approximately 0.9. Then feed stage is your stage number 5 on stage, and pressure is your 8 bar, and 0.01. Since ethane is vapor, so vapor stream should be come out from the C1 distillate, and C2 distillate, and C1 bottom is liquid. Outlet pressure is 5 bar, 3 bar, and here also 3 bar. Now all the inputs completed for C1 column. So run the simulation and see the result. After running the simulation, we can see all the ethane is coming to the top of the column, and since we have given a total flow rate of 5.29, that's why little bit of benzene is come out to the top of the C1 column. As you can see, the temperature of the column is minus 7 degree, not column, for distillate is minus 7 degree, and for water cooled condenser the temperature should be in between 45 to 50 degrees centigrade. So we have to increase the temperature of this C1 distillate. So to increase the temperature, we have to increase the distillate product. As I would increase the distillate 5.2 or 5.35, you can see temperature increases because more benzene will come out to the top of the column. Before going to anything else, first come to the setup and include fraction versus mole fraction, and give one unit, kilomole per hour, temperature in Kelvin, pressure in bar, and heat in kilowatt. Run it and change the unit set from US medbar to US1. Then you can easily see the results of all the column. As you can see, the total duty of the duty is 608 kilowatt. So to increase this temperature to approximately 48 degrees centigrade, we have to increase the distillate rate. So by doing to do the manually, we will give a design spec to it. So for design spec, go to the C1 specification, design spec, and new, and give a stage temperature of 421.15 Kelvin, that is 48 degrees centigrade for stage 1, and we will vary a distillate rate. It will be from 1 to 20, and run it. As you can see, temperature 421, not 421, actually it is too much high. It should be 321.15, 48 degrees centigrade, not 148. Okay, so the benzene come out to be 0.28 here. The purpose of this column is finished. Now we will add another column, that is the C2 column, and the bottom of the C1 column fed to the C2 column. So the work of C2 column is to separate all unconverted benzene from to the distillate, and rest from the bottom. pump and valve arrangement, it is necessary for all the C1, all the columns for the pressure, and valve is necessary for the steady state degree of freedom. Since all the column has two steady state degree of freedom, so there should be a two valve at the outlet of the each column, and according to the pressure requirement at downstream, pump may or may not be required. In C2 column, total number of trays are 24. With one reboiler, 23 total stage and one for reboiler, so 24 as given in the paper. And we will use total condenser here, and the feed tray is 6 or 8 on stage, and the pressure is 1.1 bar. So the work of this column is to let out all the benzene from the distillate. So from the C1 column, as you can see from the C1 column, the benzene is approximately 12.85. So for the C2 column, distillate rate should be approximately 12.9, and we will give a reboiler duty to it. The downstream of this, the distillate of the C2 column will fed to the reactor. Since reactor pressure is 20 bar, so from the pump pressure should be more than 20. So I will give a sufficient pressure drop from the valve, and the bottom should go to the C3 column where pressure is 1.1 bar. So the same pressure drop and pressure increase will be given to the C1 bottom. Now run the formulation. After running the simulation, as you can see, there some of ethyl benzene come out to the distillate of the C2D. So as you can see here, after giving the parameter to C2, there is some ethyl benzene in the distillate of the C2 column. So we don't want this ethyl benzene to the C2 column distillate, so we have to increase the duty. As you can increase the duty, ethyl benzene will be reduced from the distillate of the C2 column. So we will increase duty till ethyl benzene is negligible here. As I have benzene purity of 0.9913, so I will give a design spec and mole purity of benzene of 0.99 in C2D with vary of distillate rate. It will be lower bound is 1 and upper bound is 150. Then I will run the file. Yes, benzene purity is 0.99 and total flow rate is 12.9181. Okay, now third column. bottom of the C2 column will fed to the last column, and we have pump and valve combination here also. Total liquid will be sent to the pump, and valve bottom sent to the pump and valve. Since this is your product, so the pressure increase from pump is 10, and the pressure drop from the valve approximately 8, and this will be sent to the CSTR 2. So the pressure should be more than, not more than, but more than 20 bar, because the pressure of the CSTR2 is 20 bar. So from the pump is more than 20, and from the valve we will give a pressure drop such that the outlet of the valve have the same pressure as the CSTR. Now C3 column has total 29 trays and total condenser with feet at 6 number tray, and pressure is 1.1 bar. The work of C3 column is to separate ethyl benzene from diethyl benzene. So the total ethyl benzene come to the distillate, and the diethyl benzene come to the bottom. So I will give two design spec here. One is distillate to feed ratio, and other is reflux ratio. So reflux ratio I will fix at 1.1 or actually 1, and distillate to feed ratio I have to calculate from the C2 column. As you can see, and from the C2 column, ethyl benzene is 73 and benzene is approximately 0.06. So total distillate to feed ratio come out to be 74 divided by 87.85. So in C3 column, distillate to feed ratio is 0.85, and we will run the simulation. After running the simulation, as you can see, all the ethyl benzene come to the top and all the diethyl benzene come to the bottom. I will rename it to C3D and C3B, then run it again. Okay. Now after that, I have to recycle the benzene to the CSTR1. Now this benzene will recycle to the CSTR1. To recycle the benzene, first I have to put the mixer block here. So I will use like this. Now we run it. After run it, it will be converged properly, and as you can see, the total benzene come out from the outlet of the first CSTR is to be 51 mole here, and from the second CSTR total benzene come out to be 42.75. So after that, I have to calculate this benzene on the basis of the this total, that is total benzene fed to the CSTR1 and the benzene recycled from the C2 column. So we have to calculate this benzene, and the way to calculate this benzene is from the calculator block. So we will be use calculator block here. Before applying the calculator block, we have to give the value of the total benzene that is fed to the CSTR. So from the result of the S3 stream, I will input the values, the same value as from the S3. Total flow, and the temperature is 319 and 20 bar. 319, 20 bar, and benzene should be 140. And then I will apply here calculator block. So calculator block you will find from the flow sheeting option, calculator block new. So the first interface is your to define the variables. So here there are three variables: fresh, total, and recycle. The fresh value will be given by the Aspen Plus, and total and recycle will be calculated from Aspen Plus. So fresh should be the export variable, and remaining two, total and recycle, will be import variable. Stream should be the fresh benzene and component should be benzene. In total, total should be the import variable, mole flow, stream S3, and component benzene, and recycle import variable. Stream name is your S5, and benzene. Then we have to give the formula. Formula is your fresh is equal to total minus recycle, and then run and check the total value in result. Here it is 101.04. It means it has increases some benzene here, so it means our calculator block is run now in C2 block we have to prevent the leakage of benzene from the bottom. Okay, so for that I have only revolver duty in my hand, so I will increase the revolver duty and see, you can see benzene should not come from the bottom. 6.22 and then it is 5.75. okay, so as I have increases the benzene revolver duty, benzene flow rate from the bottom reduces. It is clearly seen from the simulation. Now the problem here is I have to converge the second recycle, that is a DEB recycle, to the CSTR, but before doing it I cannot apply design spec in C2 column and C3 column, because it may chances it may chance when I recycle this DEB, some of the diethyl benzene will come to the top of the C3 column. If this some of the diethyl benzene come from the C3 columns, so it means there must some unconverted benzene which must come from this column, from this stream also. So if if I put a design spec to prevent the leakage of the benzene from the C2 column, if I give this design spec, so it may there may be problem to converge this recycle stream. So first I have recycled converge this recycle stream, then I will give the design spec to the C2 and C3 column. C3 column में पहले वो देखना पड़ेगा, एथिल बेंजीन ज़्यादा आ रही है, इसको पहले एथिल बेंजीन कम करनी पड़ेगी. Where is calculator? 93 divided by 98.94, approximately 0.94. No. So before recycling the DEB stream, first I have to confirm that the maximum value should be a DEB in the recycle stream. Now I have seen that 91% is DEB in the recycle stream, so now I will recycle this stream. Now this stream is recycled. After recycling the stream, I will give now I will slowly give the purity to each of the stream. So to remove DEB from the C3D, I have to just reduce the distillate to feed ratio. As you can see, I have just decreased some value, and it is reduces. Now to reduce this benzene, I have to reduce this benzene from the C2 column. So I have to increase the duty of the column to reduce this benzene. So I will give a design spec to it. Instead of doing manually, I will give the design spec. बेंजीन इन C2B एंड वेरी करेंगे योर रिवॉल्वर ड्यूटी. will change the composition of benzene. 0.03 to 0.01. Yes, benzene is reduces and duty is increases 592. Okay, now I will reduce this to 0.05. Now again it reduces to 0.55. Again 1001. It is reduced to 0.11. Again 0.05. It is reduced to 0.055 and somewhat more 4. Okay, and the duty is 700 kilowatt. Now I have to give now I want 99.9% pure ethyl benzene in the C3 column, and I can see here is only 99.33%, so I have to reduce the distillate to feed ratio here 0.89. Yes, 0.27. Again more 0.887. So I can give two design spec here. One design spec is in bottom ethyl benzene will be 0.02% or 2%, and ethyl benzene in the top is 99.9%. So one design spec is your mole purity of ethyl benzene in bottom is 0.02, and we will change here distillate to feed ratio, which is 0.1 to 0.98. Let's see it's run or not. It will run 98% DAB and 0.02% ethyl benzene. Okay, and then I will give a design spec one more to ethyl benzene. More purity of ethyl benzene of 0.996. Right now is 0.996, I think 0.9967. Copy here and paste ethyl benzene in C3D, and we will vary here reflux ratio. Reflux ratio 0.1 to 5. Run, and then I will increase this 0.997. Here it is 0.997 and duty is 1817 and reflux is 0.88. Again increase to 0.998. Here it is 0.998. Result, heat duty is 2062, where reflux is 1.13. Again 0.999. Result, heat duty at 2850, reflux is 1.93, and we are done. So That's how you have to converge your flow sheet, and after converting your flow sheet you have to give all the material and energy balance data on the flow sheet in the report, and along with you have to give the uh, temperature plot and the composition plot for each column. I will show you how to plot the temperature plot. Just go to the column and click click on temperature. You will get the temperature plot of that column. And composition plot, just click on composition and select all. You will get the composition plot of for each column. Okay, this is your assignment for lab 7. Okay, bye and good luck.